Hi, and welcome to the next section in our boosting chapter. So this is an overview section on the, XGBoost algorithm and the XGBoost implementation, and we'll have a look at the different new ways of regularization that XGB introduces, and we'll also discuss approximate split finding and a little bit how XGBoost paralyzes and so on. So let's get started. So XGB is short for extreme gradient boosting, and it's a very popular open source and also quite scalable tree boosting system. It's implemented in C++. It's quite an efficient implementation, and provides many different interfaces to other programming languages, especially Python and R. Contains a faster, not super difficult parallel approximate split finding algorithm to speed up the split finding in the tree training procedure. When we fit our trees in the gradient boosting ensemble, it will introduce 3 new, or maybe even 4 new ways of, if we count Dart, additional regularization techniques. It uses feature and data subsampling. We have at least covered data subsampling already in the form of stochastic gradient boosting, and we discussed feature subsampling when we discussed the random forest, and this idea is kind of incorporated now also into the boosting algorithm. It's parallelized. It provides various interfaces to cluster parallelization frameworks, and also features GPU support, and it's highly optimized, and it often achieves top performance in terms of predictive power in benchmarks. But it usually needs quite an extra effort for tuning because it features quite a high amount of hyperparameters. So here are the extra regularization terms that XGBoost introduces. So when we add in our new base learner here during the mth iteration, we don't only do this in a pure risk minimizing fashion. We already know that regularization can be beneficial to avoid overfitting, and XGBoost uses not only the L1 or L2 but both penalties, and it uses these penalties as a vector penalty applied to all of the constant values of our current tree that we're adding into the ensemble. So this CM vector here is the vector of all heights of our leaf nodes. And it also additionally penalizes the number of leaf nodes in our tree as a way to penalize the structural complexity of the tree or the depth of the tree. A few words on the tree growing algorithm, or how we grow trees in XGBoost. So trees are usually grown in a balanced fashion to maximal depth, and this depth parameter is a hyperparameter that we again can use to control the interaction order of our resulting boosting model. These trees, they're fully expanded in a balanced fashion, and leaves are split even if no improvement happens. But at the end, each split that did not improve the risk is then pruned. So you can see this here, I guess. So we have denoted here the various numerical qualities of our nodes in terms of the associated risk values with these nodes. And you can see here that if they are like negative numbers, like here, we would later on prune these nodes and do this in a recursive fashion to then create an unbalanced tree at the end after pruning. As I've said, XGBoost uses now 2 forms of data subsampling. It just uses the regular stochastic gradient boosting technique, which just means in every iteration we use a random subsampling of training data points to fit our new model. We discussed this before, but it now also steals the feature subsampling technique from the random forest. So similar as the m-try value in a random forest, we now have a hyperparameter that controls how many features in a random subset are used for split finding, and this fraction of features can be randomly sampled either for each tree, so at the beginning of fitting a new tree, for a certain level of a tree, or for an individual split. And this feature subsampling speeds up training even further, and it can create a more diverse ensemble, and quite often this will perform better on average. Here's a slide on the approximate split finding algorithms that can be used in XGBoost. So there are two versions of this, a simpler, faster global one and a more computationally intensive local one. So the idea is to speed up the tree building for large data sets. And, how do we usually do that? I mean, we sort our data, our feature values. So let's assume that, 10K, we have an N of 10K, so 10,000 observations. Then we have, 10,000, maybe minus one, I guess, potential split points. But if the data set is really, really large, it's probably not that necessary to really try out each individual split point between each pair of observations in this ranked order to find the absolutely best split point. I guess we can also move through the percentiles with larger steps of the empirical distribution of the feature. So what that means is just like fancy terminology for we take our feature values here for, feature X, we rank them, we sort them, and we would now move through this here, usually in steps of size 1 to try out in each individual split point. And what we are now going to do is we're just taking larger steps. So we can take steps of 2 or, steps of 4, and this is what we mean here that we use these percentiles of the empirical distribution of each feature. Okay, here you can see the distribution, and what we can now do is that we either define these split points on the empirical distribution of the feature at the beginning before we run our tree building algorithm, and then we never recompute that. And you see that here on the left hand side. So you could see here the potential split points that would be tried out in the search, and these are these blue dotted lines here, and then maybe this one here is the best. So take that red line here as a split point. Problem is, if we split at that point now and we stay with these split points, some of them actually might not contain any data at all, right? Because the data is now divided into a left and into a right branch, so that might not really be optimal. It's probably a bit better to do this local recomputation, which means we have to recompute these percentiles here after each split, okay? And this, some people also call this histogram-based gradient boosting. I guess it mainly actually refers to, it's mainly histogram-based tree fitting, I guess. And you could do this, I guess, also for every algorithm that's tree-based. So you can do this in a regular tree, or you can do this in a random forest. You can see here, XGBoost is a little bit like, kind of a Frankenstein type of library. It tries to kind of steal every idea from every other machine learning technique and to kind of patch them together. So it also steals the dropout technique that you may or may not know from deep learning. So in neural networks, when we train them, so what we often do during gradient descent is that we don't adapt and perform the computation with respect to all neurons, but we kind of make some of the neurons inactive in each iteration. And we try to do something similar here now in gradient boosting. So and this is called DART, dropout additive regression trees. So let's assume we are in iteration M, and we want to construct here our new base learner BM. And in order to construct this base learner, what do we need to do? where we need to compute the vector of pseudo-residuals, and we need to fit our B hat against that vector of pseudo-residuals. In order to compute the vector of pseudo-residuals, we need to insert into the formula of the pseudo-residuals the prediction of our current ensemble, which is of size m-1. And we don't do this in the regular fashion. We just, push our observations through that m-1 size ensemble, but we will only use a random subset of that ensemble. So we'll use a p-drop percentage of that ensemble. I don't know if p-drop would be 0.7, we would use 70% of this ensemble, and we in a uniform fashion, we sample some indices, we sample some elements from our current ensemble and only use these to compute the prediction. It's clear that if we do that, there's a certain underscaling of this computed prediction, and as in deep learning, we have to avoid overshot predictions now in the ensemble, and we don't do this here at test time. We do this still at training time. So we do a rescaling, but we do this at the end of the current iteration when we construct this guy here and we add this into the ensemble. What we do is we rescale the added in ensemble member by this term here, and we also downscale all of the touched ensemble members that were in our random subsample D that we used here to compute the dropped out prediction, or the dropout prediction version of f hat. And there's an interesting thing we can now also see if we study the extreme values of p drop. So if we set p drop to 0, we never subsample that guy here, and that in that case, basically all of these terms here will become basically 1. We don't do any rescaling, and then we are doing ordinary gradient boosting. So that's, I guess, pretty obvious. So just setting p drop to 0, nothing happens. We are back to ordinary gradient boosting. Not that interesting. But if we set p drop to 1, then all base learners are trained independently and they are all equally weighted. And in that case, our model is actually quite similar to random forest. So we now can do something like a smooth interpolation between regular traditional gradient boosting and the random forest by controlling this interpolation between the algorithms through that p drop parameter. I already said XGBoost can also be nicely parallelized. So for gradient boosting, that's actually not very obvious how to do this because the algorithm, instead of the random forest algorithm, is inherently sequential. So it's not really embarrassingly parallel as an algorithm. So it's not super obvious how to parallelize that. But what you can do is you can actually parallelize the building, the construction of the base learners, and we do that by seeing that the data sorting and the split evaluations in different branches of the tree base learners can be computed in parallel. And we often also use here, or we do use in the XGBoost implementation efficient block data structures to make this even more efficient. And XGBoost is also implemented with support for GPU hardware, and that again can give us a huge performance boost in training time. I want to stop here with tabular overview of the most important hyperparameters of XGBoost. We've also tried to give some typical ranges for these hyperparameters that these may vary. So take this with a grain of salt. So we might have to adapt those for your own applications. We also try to write down whether you should optimize these parameters on log scale and the default values here from the implementation. So you can see here the eta parameter, which is the learning rate of boosting, the n rounds parameter that controls the number of boosting iterations, the gamma parameter, minimum loss reduction required to make a further partition of a leaf node of a tree, max depth of our trees. We discussed that. We discussed the column sampling, and you see here the subsampling ratios. Here you have the subsampling ratios for on rows for the data, and different weightings for L2 and L1 regularization and so on. And I guess we are even missing a few hyperparameters, so I guess we are missing the dropout. And if you look into the implementation of XGBoost, you will see that it actually has quite a few more parameters, also quite a few technical parameters that control technical issues of the fitting algorithms and parallelization and so on.